Now it's recording? Oh, okay.
Okay. So this afternoon we have Pietro Sparoni Benedictio, who is talking this. Let's go.
Hello everybody and welcome. Thank you, Inma, for inviting me. I was here doing the easy course in '98 and I was starting to work on artificial chemistries at the time. And I got some results and then I started presenting those results. And I presented them, and I presented them again, and I presented them again. And nobody seemed to actually get them, or I was explaining them very, very badly. So the results were piling up and getting together, and I did my PhD, and the PhD was looking good, and they were starting to be applied, but the results were coming from the field of artificial life, artificial chemistries and artificial life, and they were not being used by this field. So I eventually, when I went at the ECOL conference this year, I realized that my main problem at this point was not a problem of reaching new results, but was about communicating the results that were already there. So really going back and explaining everything in a really, really clear way. And that's what I did over here. Just the basics. I will not enter into any technicality over here. You can find the technicalities on the paper. You can get the paper from my own page. There's no problem. I will assume that you know pretty much what is an ordinary differential equations, and that's about from where I'm going to start. Things can be explained easily, simply, or in a complex way. You cannot bring them more simply than a certain level. There is a certain level beyond which you're starting to lose parts of the system of what you're actually trying to explain. And so we are trying to keep it as simple as possible, exactly as possible. So normally when we think about artificial life, we think about many different disciplines, and we normally think about well, there is the whole part about replicators, and where, if you look at Avida and Tierra, they're looking at one kind of agent that generates two kinds of itself with some mutations. And then there is the whole part about hypercycles and about parabolic equations that generate hyperbolic growth. And so where you have two agents that come together and generate a third agent. They seem quite similar. Actually, there are some changes in the way the system works, so that in the first case, if you have a mutation that is very positive for the system, it will spread. In the second case, it's much harder. There are some conditions under which it works and some other under which it does not work. And there's quite a lot of bibliography on this in artificial life and in theoretical biology. And then you have all those systems like Tierra, where you have an asexual growth, like in the first case, but then you also have parasites. This is another kind of system. Now, as you see, there is a reaction network, a way in which we write those reactions, which is, it's actually very similar from one to the other. And finally, well, in this case, we were requiring that elements to react, to generate copies of themselves. They had to do this in a linear way, in an asexual way. If you don't require this, you have a more general system. Okay, fair enough. Whoops. Why did I want it forward? Okay, sorry. Something weird with this mouse. Okay, then we have another kind of system, which are artificial chemistries. Now, artificial chemistries are similar to the one above. There is only one little difference, that when two molecules come together, two agents come together, they can generate something new. So where over here, every molecule on the right, everything that was on the right, you could find it on the left. Over here is not always this the case. You have A plus B would generate a new molecule, F, a function of A and B. And of course you have the equations, and the equations are somehow similar, except that there's a parenthesis missing. But apart from that, they are precise. And then you have, okay, these kind of artificial chemistries were developed and brought forward by Fontana. And when we started studying them from a formal way, a lot of problems came out. Because the way in which molecules over here are destroyed is linked to the production of molecules. So how does it actually work over here? You have a bag of molecules. You take two molecules, you bang them together, you generate a new molecule, and you put it in the bag. And you also put the two molecules in the bag. So you took two molecules and you throw in three molecules. Now the bag is expanding. So you have to throw away another molecule so that the number of molecules inside there is always fixed. But in this way, you are connecting the outflow of molecules with the fact that it's possible for molecules to replicate. We will see in this talk that this brings to a certain number of mathematical problems. So a simpler system is just a system that unbundles those two, and where while this reaction is happening at its own speed, at maybe lower speed you have molecules that are being thrown out, but because each molecule has a certain probability of being thrown out, when the quantity of molecule is big enough, the two speed will balance each other, and the whole system will remain with a certain number of molecules. Essentially, apart from this element, and those two systems are pretty much equivalent. And then you have another kind of system that we discover, where instead of having what we are up to now, you tended to have a catalytic system. That is, molecule acted and were not used up in the reaction. Then you can have other kind of system where this is not true. And the equations, as you see, are quite similar, except that now the molecules that are on the left do not appear on the right. As you see over here, they always appear on the right, except this X, but this X is meant not to appear. It is this outflow, and the result does not depend on this X. And then you have general chemistry. You know, we've been going through more and more general system from one to the other. Okay, so you would say that pretty much you can cover most of artificial life around here. And one of the things that a lot of people are interested in artificial life is novelty. So we're not just interested in how systems behave over there, we're interested in how something new appears and how the system changes and goes and follows those new and changes qualitatively. The key word is qualitatively. So normal science goes and tries quantitative studies. We already know what's there. We want to actually find out how much of the various elements. The problem is, what if we don't even know what is there? What if we go to a continent and we don't even know what animals are there? First we need to know what's there, and then we can start to measure how much those elements are there. So this is going pretty much to summarize the work that needs to be done. So you have mutations, and you have intrinsic novelty. You have novelty arriving. And the novelty arrives either through mutations, and I don't have, I think, to present here mutation, or to what we call intrinsic novelty. What is intrinsic novelty is when you have two molecules, they come together and they generate something new, a molecule that is not there. So if we go back and look to that table we were seeing before, oh gosh, sorry. If we go back and look to that table that we were seeing before, you get intrinsic novelty from here on. You don't have intrinsic novelty above. So in any case, those are different ways to get novelty, but then the novelty has to spread, it has to stabilize, whatever that means. We have not yet explained that. But then, and this is somehow a system, you know, it can continue over here. But then we want to actually track how the system gets one novelty after the other, how it changes, how it modifies and goes from one type of system to another type of system. This is one way of following it. Another is to make a map. Another is to map the whole set of possibilities. And then to say, okay, if I'm here, I will go here. If I'm here, I will go here. And so on. And we'll see that those are actually very linked. If you have one, you will easily have the other. The other way around doesn't work so well. So, as we said, intrinsic novelty, we only get it in this kind of system. Mutation, we can get it in all kind of system. And there is something else. Well, there is something else. There is a different speed in this kind of novelty. When we are speaking about intrinsic novelty, we expect this novelty to be fast respect to the experiment. That is, when the system is stabilizing, we want the intrinsic novelty to play its effect until it kind of stabilizes. And then once it has stabilized, we hit the system with a mutation, and we expect the system to go somewhere else and then stabilize itself, generate all the intrinsic novelty again, and then stabilize again. So there is a difference in the time scale in which those two novelty act one respect to the other. Now, to study how novelty work around, essentially, we need to find something which is equivalent to what has been done in science using ordinary differential equations. When you're using ordinary differential equations, you are actually making a quantitative study of a system. And then you know there is a phase space, there are fixed points, there are attractors, basins of attractions, and then there is a trajectory. Once you know all this, then the trajectory is pretty easy to calculate. As I said, I kind of expect people to know what is an ordinary differential equation, the phase space, and so on. I'll go very, very, very rapidly. A phase space given a dynamical system, a phase space is a space that represents the possible states of the system. Every point that I pick in the phase space represents a state of the system. So if I have a pendulum, the phase space would be a two-dimensional space, because every position of the pendulum can be represented by the position on the x-axis and the speed. So those are two numbers, I can put them in a two-dimensional space. And phase space normally have more than two dimensions. When you're lucky, they have a finite number of dimensions. And this is essentially, we need to map, to study this part, will be the qualitative side of this table. Okay, so let's start. Now, on the left side we have the phase space. On the right side we'll have the space of molecules. Over here, each point over here tells us a quantitative state of the system, is able to tell us where the system is from a quantitative point of view. Over here, each point represents what molecules are there, what agents are there, what kind of system is there. So, over here, if we have a system of an equation, and the equations are the same for the two systems. A system of an equation will have Rn to represent it, R plus n, because molecules are only positive or equal to 0. You don't have negative molecules. On the other side, well, if you have n molecules, you have the set of those molecules, and then you have 2 elevated to s as the space of all possible molecules. So this is the space of all possible sets of molecules. You have a bag of different molecules, you take a subset, this is one of those elements. If you have 5 molecules, you have 2 elevated to 5 possible subset that you can create. Let's make, oh, I need to remember to take away the fact of going backward. Okay. So let's give the example with n equal to 3, because it's about the maximum we can visualize easily. Well, with n equal to 3, R plus 3, I don't know if it can be seen because it's very gray, but essentially it's a 3-dimensional space. Okay? On the other side, we have 2 elevated to a set of 3 elements, and this creates the hypercube in 3 dimensions, which is commonly called a cube. If you don't see, maybe come near.
No, just a question. Why is it on the phase space?
Yeah.
Why is it real value? Is it? I may have missed a minute. Was it the number of molecules?
It's a number of molecules, but what we are comparing here is the way in which you use ordinary differential equations on the one side. So when you're using ordinary differential equation, you tend to use a continuous approximation.
So that's just why you're not using the natural numbers to n then?
No, I'm not using z.
Okay.
I'm using, but essentially you can do the same thing with z. That's absolutely.
So it's just like amounts, and so we're looking at like the population size or something.
Yes.
Yeah. Okay.
Let me finish the slide before going on question on this slide.
Okay.
So every point over here represents a space or a subspace over here. There are 8 points over here, which means there are 8 spaces or subspaces over here. Can you see them? Well, first of all, we have the empty set. And the empty set represents, of course, the origin. So if we have no molecules, that it's represented over there, and this is represented over here. Now, if we have only X molecules and nothing else, over here it would be represented as something along this axis, whereas over here it means that we are on this point over here. If we have only Y, we are on this axis. If we have only Z, we are on this other axis, and then we put them together. If we have Z and X, we are on this flat plane down here. If we have Y and Z, we are on this other plane over here. If we have X and Y, we are on this other plane. And if we have all kinds of molecules that are present, X, Y, and Z, well, then we are in the space in between those walls. It's like we have this room, and we are in the space inside. We are not on the walls, and we are not on the line between the walls. Now, this is okay for n is equal to 3. Now, we destroy this, and we ask a bigger question. What if n is equal to 5,000? Yeah, I had a new program to make the presentation, so I got a little bit of fun. So this is nothing, you're going to see later on. So what if n is equal to 5,000? So if n is equal to 5,000, we are speaking about a 5,000 dimensional space. That's difficult to visualize. I mean, the mathematician that I knew that were able to visualize more, were able to go to n equal 5, a 5-dimensional space they could. More than that is difficult, and 5,000 is really hard. So, and we're still on finite. Oh, sorry, you had a question.
Yeah, it was just about the notation you used there, the modulus of S is equal to 2 to the modulus of S.
Yes.
Not quite understanding.
Okay, that's a way of representing the set of all subsets in S. It's just in mathematics sometimes is called in this way, but it's the set of all subsets of S.
Okay, I'll look that up later.
Yes, sure. So now we've spoken about what is the space of molecules. We want to go one step forward and ask ourselves what are the equivalent of fixed points. So what is a fixed point? A point in the phase space, such that if the system is there at time t equals 0, then it will still be there at time T con E with E bigger than 0. So, well, what you do normally is you have your equation, you define that the first derivatives are equal to 0, you solve it, you get some point, you find what are the eigenvalues and the eigenvectors over there, and then you find out if the point is attractive or not attractive and what's going on. That's usual ordinary differential equation stuff. And people don't like eigenvalues and eigenvectors, but that's what they do. On the qualitative side, we'll define it in some way which is pretty much equivalent. A point in the molecular space, because now we are on this kind of hypercube of 3,000 or 5,000 dimensions, and such that if the system is there on this point at a certain time, it will still be there later on. So we want a set of molecules that does not change qualitatively as time goes by. So we have our space, and some of those points will be spatial because they will be fixed, the equivalent of fixed points. So we can kind of find those points, and then we find something about those points. We find that for.
Can I just interrupt you for a moment, Pietro? Just to clarify, or make sure I got clear, I think on the right here, those are types of molecules, aren't they?
Yeah.
So each of those dots there is a type of molecule?
Nope. No? Each of those dots is a set of possible types of molecules.
Right.
So this will be no molecule at all. This will be only molecules of type X, this of type Y, this of type Z. But here you don't have another type of molecule. Here you have the combination of those two. So here you have X and Z. Here you have X and Y. Here you have Z and Y. And here you have 3 molecules at the same time.
Okay, that's fine. And
Okay.
on the left, you've got concentrations.
On the left, you've got concentrations. Yes, you're ignoring the concentration when you move. You only want to know if the concentration is bigger than 0 or is equal to 0.
Right.
So some of those points will be spatial. Now, what do we want? Essentially, for those points to not generate, to be fixed from our point of view. Well, we want, if we have one of those points, we want that it doesn't generate nothing outside. So no new external molecule is generated. They can generate molecules of the same type. They cannot generate, you know, you have giraffe and zebra in some place and you don't want them to reproduce and generate a lion. If they generate a lion, that's kind of odd. It means that the system is not closed. Or you have horses and, what's the name in English?
Donkeys.
Donkeys, and you get them together and suddenly you have something new. And then the system would not satisfy this principle. This principle is called the closure. It's a mathematical principle. You can find it in any algebraic test. It means text. It means you take elements over there, they can interact according to a certain operation, and the result will always be inside there. Now on the other side, we want that we are not losing every molecule. So we want that no existing molecule is destroyed. Now, some of you will know all this theory from Walter Fontana. And so Walter Fontana had the description over here, the closure. It was like this. He was presenting this in this way. In fact, my work has been very, very strongly influenced by Walter Fontana. I'm extremely indebted with him. And but over here, he did not have that no existing molecule is destroyed. Over here, he had every molecule can be generated. Okay, we'll find out why there is this difference. So we can connect those elements, we take away the rest of the molecules, and we can find a smaller set. So those we can actually see system with only those points spatial. For the moment, we just leave it over there. I'll explain more later on. I'm just putting in ideas that I will use later on. So again, what if n is equal to 5,000? Now let's try to see how those two concepts plays in respect to all those systems, because the concepts are absolutely general, but then it gets applied to systems in a different way depending on the particular kind of system. Well, first of all, this is the kind of system that was presented by Walter Fontana, and his definition of closure is you get a set of molecules, so you get a bag, and it's closed. If given two molecules inside here, you interact them, and the result is still inside the bag. It's still something of the type that are inside the bag. And on the other side, the self-maintaining, it was, well, you take your bag, and you take one molecule, and you look inside, and if you find molecules inside this bag, even of the same type or others, that reproduce between them, reacting between them, can regenerate this one, then we call this molecule a self-maintaining molecule. There's some problem with this definition, but not so many. So, okay, first of all, with replicators, the concept of closure is pretty much useless, because replicators' equations are always closed. Whatever you find on the right is always on the left, so you don't even need to calculate it, which means if you're looking at your lattice, your partially post-set, partially ordered set of all type of molecules, well, the partially ordered set of all type of closed molecules, of the set of closed molecules is the same. So we're not gaining nothing over here. But over here, well, we can find a subset, some of those sets will be spatial, and the definition for those two kind of systems is the same one of Walter Fontana. Let me not repeat it, please. And over here, well, it's slightly more complex just because the operation is more complex, but the concept is the same. You take some molecule inside, you react them, they only generate things that are over there. You're not generating nothing new. Now, let's look at the concept of self-maintenance. Now, first of all, where do we need to check if a molecule is being self-maintaining, is not going to be destroyed? Well, that depends if that molecule can be destroyed or not. I mean, in some systems, some molecules are not going to be destroyed at all. For example, you are studying a system of the cell, and you have the molecule of DNA, and you know, yes, there can be errors, but in your system it's kind of simple enough that you don't have errors in the DNA, and you're looking at a time scale which is between one reproduction and the other. Now, the molecule of DNA will not be destroyed by anything of the molecules that are over there. So you don't need to check that this molecule is not going to be destroyed, because nothing will destroy it. So the first requirement that we make is that we only check for self-maintenance on the molecules, and only on the molecules that are being destroyed in some way, either because there is an outflux or because a reaction destroys them. If there are non-catalytic molecules, they can be destroyed. If not, well, there is an outflux, and then you have to actually, for example, all those systems, this system and those systems, have an outflux that destroys every single molecule. Every molecule has an outflux, is being destroyed at a certain speed. And so you need to actually check it for all the molecules over here. Now, what about this kind of system? This is the original kind of system from which Walter Fontana started working, and there has been a lot of confusion out there, with people coming out with papers and saying that this kind of system really do not lead to this kind of fixed point, which are called organizations. Because of it. Now, let me clarify the mathematics behind this once and for all, and it's being videotaped, so there will be no doubt about it. We want that no molecule is being destroyed, and we want this because we want the set of molecules that are going to be fixed, that represent fixed point from a qualitative point of view. Now, if you are taking, as long as there are reactions in your set, then all the molecules are being destroyed. So you are essentially behaving like those systems over here. If you take a bag which has, you have a bag and you have molecules inside, but those molecules do not react with each other. They are all elastic. They just, they don't like each other, and they avoid each other, and they don't react. then not only you don't have new molecules because there is no reactions, but you don't also have molecules that are being destroyed, because in this kind of system, to have something being destroyed, it has to be entangled with a reaction. So every set of molecules where all the molecules are elastic between each other is one of those fixed points. It is, in a trivial way, always. No cases that no other cases. Okay, and then we'll see that for more complex system, being self-maintaining is what we're requiring over here is not strong enough. We need to actually make a stronger requirement. But this is more complex, so let's go forward. Now, in those two cases, in linear relation and autocatalytic, everything is not only everything is closed, but everything is always also self-maintaining. Because yes, every molecule is being destroyed, but every molecule is also being generated. Every molecule that is present generates copies of itself. So this is okay. Yeah, you could have a problem when you have only one of those of a particular kind of molecule. Yeah, let's ignore this case. Let's put it under the rug right now. The really interesting cases start to be when we are looking at Parasite. When we are starting to look at Parasite, you have your, well, this is still an hypercube, you know, you have the hypercube of the molecules that do not react with each other, that do not react with each other but generate copies of themselves, and then you have a parasite. Well, essentially, this will, if you make the system, it will come out as something, a sort of extension, a sort of like you have a cube and another cube attached to it. So, from a formal way, we say that a set is a self-maintaining if and only if, for every molecule that is there, either you can reproduce it over there, or there is another molecule that will reproduce it. So, that's okay. This will generate, this could be a good definition of self-maintenance in this particular case. And then over here is the same definition, a little bit more complex, because the definition is more, well, it's just the second part, actually is even simpler. And over here is the same definition of Walter Fontana. So, and over here is again the same definition, except that instead of taking only two molecules, you have n molecules. Yeah, I only wrote 2 over here, but you actually have n molecules. Now, notice one thing. Here we call it self-maintenance, here we call it semi-self-maintenance. Because having this, what Walter Fontana presented in, that was in 1990 or 1980, that's actually not going to be enough in complex system. What do I mean? If you have a set, his system was catalytic, so he did not have these problems. But in the moment in which you want to generalize his concept, and you want to get those concepts to a wider audience and to a wider set of system, that's not enough. Because if you have a bag, if you have a bag of system, of molecule, and molecule A generates molecule B generates molecule C generates molecule A, so this is a nice circle and it's self-maintaining. But then you have a decay of one of those, and those molecules are non-catalytic. Then you have 100A, this gives you 100B, which gives you 100C, which gives you 99A. So every time you go on a cycle, you're actually losing some of those molecules. You don't want that to happen. So the definition of self-maintenance is that there is a flux, and you can look in the paper the formal definition that uses stoichiometric metrics. There is a flux among the reactions, there is a speed of all the reactions inside the bag, such that no molecule is being destroyed and no molecule is being generated. So there have to be a solution. Now, it can be proven, I have proven it is in my PhD, which can be downloaded. This implies this. Over here, the two concepts are the same. Okay, so just simply normally what you would have, you have those two concepts, closure and self-maintenance. Self-maintenance is divided by itself in semi-self-maintenance and self-maintenance. Here is the definition of closure, and this is the definition of semi-self-maintenance and self-maintenance. When something has those two elements, is one of those special points, and we call it semi-organization. And when something has the whole thing, those are organizations. This is what we are after. This, now you can kind of ignore all the rest. You don't care about all those details. The important thing is there are some points. Those points are equivalent to the fixed point in the quantitative case, and we can calculate those points, and we can calculate this. Some of those points, the semi-organization can be calculated in a fully algebraic way, so in a rapid way. You don't have to solve a very complex equation. It's very, very simple. Now, some of those points will have an extra quality, and you have to go and pick those points and test those points one by one. But they are much less than before. If you had 5,000 dimension, you had maybe 2 elevated to 5,000 possible state. You don't have to test all of those. The semi-organizations will be much less.
So can I just, this is possibly quite an important point to clarify, but
Please.
could these things really exist in a bag? Because thermodynamically...
In a, sorry?
In a bag, in a sealed, closed bag. Because thermodynamically you couldn't have any kind of ongoing reactions without some kind of flow, feed flow.
Yeah, we are studying those inside the metabolic of cells. We are studying those in the. You can have an input of molecules. So, for example, we are studying those in the atmospheric chemistry of a planet, and the input over there, the energy will come from light, and light heating molecules and making them react. So definitely you can. And
it's not a question of whether you can, it's a question of whether it's possible if you don't. That was the question.
Well, you would have to have some input in the form of energy.
Yeah, exactly. Yeah, that was the.
That's okay. It all works even if you have input.
No, but does it work if you don't? That was the question then.
Well.
Because it shouldn't do, right? You shouldn't. You shouldn't be able to have anything.
Well, you would have that everything. Well, yes and no. I mean, the points are. I mean, most of the system that you are studying, which has those and where there is no energy calculated, the energy is intrinsic. So somehow you like in Fontana, he assumes that there is a flow of of DNA pieces and of big molecules and so on. As I said, this is so no. Essentially, you're actually using the fact that you're applying it to system where the energy is assumed, or you can actually model the energy directly as an input, as particular molecules that then will break up other molecules and so on. So you can do it in both ways, and it works. Now, if you find a whole set of places where everything is elastic, well, then here you go. You have everything which is everything is one of those fixed points, and
Can I make a comment on this? I think, Pietro, when you find your fixed point and you solve your differential equations, I think there'll be some rate constants on those, won't there?
Yeah.
So there's some implications of energy and thermodynamics in the values of the rate constants.
Absolutely. Now, let's go on. If you have a quantitative and qualitative, so the equivalent of the fixed point are the organizations. All the things that we've said, closure, semi-self-maintenance, self-maintenance, those are technical details. You don't really need them. You need them when you want to calculate it. You don't need it to understand the rest of the talk. So if you got lost in those, just this is a good moment to come back and follow us again. When I was doing mathematics and I was getting a degree in mathematics, some lessons were particularly boring. I would follow the lesson until it would start a theorem, I would hear the definition of the theorem, I would fall asleep during the whole where it would, the theorem would be proven, I would get awake after, and I would follow the rest. And it kind of worked, and I got my degree somehow. So, I see Man is worried because some of the students are actually getting this. So, if we have the organizations, this is the space, and then, as we know, each of those points represent a subspace over there. Some of those points are closed. So the points are, a subset of those. And then some of those points are semi-self-maintaining. Some of those points, some of the semi-self-maintaining are self-maintaining. Some of the points are closed and self-maintaining, and those are the organizations. So now we take away everything else, and the only thing that remains are the organizations. So as I said, the only thing that remains are the organizations. So this that remains over there is it was a pose set, a partially ordered set, and but it has other qualities. It's actually mathematically a lattice. Means that every time that you take, every moment you take two elements in this pose set, there are two operations which are normally called union and intersection. You can take the union of those 2 points, and this will be another pose set. You can take the intersection of those 2 points, and this will be another pose set. Now, when I call them this union and intersection, I do not mean set union or set intersection. For example, you have a molecule A and B over here. You have molecules C and D over here. I put them together, so there will be one and only one organization that is connected to AB plus CD. But it's not necessarily AB plus CD. Might be something else. Maybe AB interacting with CD generates molecule E, and then we have ABCDE, which is the organization. But there is an operation. It's possible to use this to find out this lattice. This is important. This is really important. This is why this is important. Because then you don't need to calculate. You're trying to find which points are spatial, and you don't need to calculate them all. You don't need to test them all. You just have to test some at the beginning and then put them together, and then try others. They might not give you all the points, but they will give you many of those points. And this is already quite a map of what you're studying. You cannot do this always. Now, let's go forward. And then you have semi-self-maintenance and self-maintenance, and they also, well, over here we said that the lattice is trivial, is the hypercube in n dimension, because closure here is trivial. Obviously, closure is also, self-maintenance here is also trivial. The replicator in every closed set is, every set of replicators is closed. Every set of only replicators with no parasite is also self-maintaining. This is trivial. Then here you get lattices. I won't go through the various definitions, through all the various elements. But the lattice over here are very ordered. They are nearly always distributive. I can enter into when they are, when they're not. Let's just leave it at that. Now notice something over here. Here, for chemistry, you cannot do it. So for chemistry, if you're studying just a chemical system, something where, where there is not an outflux of every molecule, then it's not a partially ordered set. It's not a lattice, it's just a partially ordered set. And of course, this is what we are actually after. This over here, we want to know the organizations. What is the structure of those fixed points what is the algebraic structure of those fixed points? And they are a lattice. From this point onward to here, from a set of replicators with parasite to a consistent reaction system, which is the system that you find inside a biological cell. From here to here, everything is a lattice. So if you're studying any of those systems, you probably should go and use and find out what is the lattice of these fixed points. Why? Well, I think I'll tell you the why later, I don't remember. So, again, now we want to know something more. We want to know the relation between the fixed point and the organizations. So the organizations are over here, fixed points are over there, and there is a theorem. The theorem, you can find it again in the papers in my PhD, you can find it in another paper, it was out already in 2005. Every fixed point is an instance of an organization. So if you have an ordinary differential equation, and the ordinary differential equation has a fixed point, and then you take the set of molecules that are present, that are higher than 0, over there, in this fixed point, you just take them as a set, this set will be a fixed point, will be an organization, which is the fixed point of, from a qualitative point of view. So let's give some example, because we are starting to get really abstract, and I know that not everybody is able to follow. We know that this relates to the 8 spaces over here. We have already seen this. Now let's imagine that we have this lattice here. Now where will the fixed point be over here? Well, we start. You see the origin? Here the origin is connected to here. Now we can imagine, I don't know what this system is, we're just making an example. We can imagine that there is a fixed point just inside here, just in the origin, and it's attractive. I'm sure you can find a lot of systems where there is a fixed point. Well, the origin is nearly always a fixed point, in fact. It's not always attractive, but it's nearly always a fixed point. Unless you have input. Okay, let's take a second one. This is the kind of, nice, cool things that this program permitted me to do. So, we look at this other one, and this other one, oops, goes over here. So what does this represent? It represents all this line. Now there is a fixed point somewhere over there. And then there is another one just over here. And this one might generate a fixed point over here. Now, wait a second. Every fixed point is an instance of an organization. The opposite is not necessarily true. You can have organizations that do not have fixed points inside. And we'll give this example for this other organization, which will naturally map into this space in the middle, and I'm not going to draw a fixed point in the middle. Besides that, I wouldn't know how to do it, but just to give an idea that this is not a one-to-one relation. Also, it's not a one-to-one because you can have more than one fixed point in an organization. But every fixed point is in an organization. So again, suppose you have your system with 5,000 molecules and you want to study it and you want to find the fixed point. Are you going to search in all the space? No. You are going to look for the lattice of organization, which you do by looking for the lattice of semi-organization, which is algebraic. You apply the algebra, it's all mechanic, and it will come out with a set of possibilities. Then you study those sets and you find out which of those can have a fixed, can be an organization. And this will be a subset of this. And there you look for the organization. You don't look everywhere. So you actually now can tackle systems that you could not tackle before. Those things came out in 2005, 2007. So let's give an example. This is only 15 molecules. And this is the standard artificial chemistry. This is the standard as Walter Fontana used to do it. This one is from, we call it Entop, is from Dietrich. And by the way, all this theory, we did it together, me and Peter Dietrich. He was my supervisor in my PhD. And there's a lot of other people that got actually involved, and we'll see the publications at the end. So this is a reaction system. It means is a way to represent the reaction system. if you have a number at a certain point, for example, this 3, under 3 and under 6 means molecule 6, when it reacts with molecule 3, will generate a molecule 3. And this is exactly the kind of system we were saying before, where two molecules generate a new molecule in a catalytic way, and then a random molecule is taken away. Okay, so this is just a system like that. So now we want to know what are the organizations over here, and I will spare you the detail of the calculations, but essentially those are all the organizations that are present over there. Those are 54 organizations, and they can be represented in a nice lattice, which is this one. If you take two of those points, you can define their union. For example, this, well, this is under here, so the union of this and this will be this one. But for example, the union of this and this will be this one above, and the intersection will be the smallest, the biggest organization which is inside both of them. And so on. This is a theory of lattices algebra. You can find it. And I'm sure you can find people who can explain you this. It's pretty easy. It's really the easiest part of algebra. So, and it's pretty fun. You can find lattices everywhere. Eventually you start to see them everywhere. So we have the reaction network. We have the organizations. And what do we have? We have 16 molecules over here. We have 2 elevated to 16 possible sets. So we have 65,536 dimension that this space has. And it's a small one. No, sorry, 16 dimension. And 65,536 points. I wanted to see if you were following. And out of those 65,000 possible points, only 54 are organizations. So we've moved from a space of those 65,000 possibilities to only 54. And because with this kind of system, semi-organizations and organizations are the same thing, you don't even need to calculate something which is not algebraic. You just do this, those 54, you just found them with using some algebra. You'll find what the algebra is. So, okay, phase space, space of molecules. Fixed points is equivalent to organizations. Every fixed point is an instance of an organization. Now we go to the next one. Attractor, basin of attraction, and then we're going to go to the trajectory. So, what's the basin of attraction? Here is our nice system. Well, this is what the basin of attraction is in an ordinary differential equation. Where, well, you have some fixed point and some limit cycles. And essentially, in yellow, you have the basin of attraction of a particular attractive point, which either is this limit cycle over here or is a fixed point in the middle. I am not really sure because I don't know what are the equations. I downloaded this from the internet. But look over here. This is another basin of attraction, and this is another basin of attraction. So essentially, wherever you are, unless you're in a fixed point, unless you're in a limit cycle, you are in a basin of attraction of something. So how do we get to those basin of attraction? Essentially, we want a function that associates to each point of the space of the space an attractor, and possibly the attractor to which the point will eventually go. So from here, I go here, there is an arrow, and it works. Well, over here we have something similar. Those are called the generators. It means, suppose that we have a particular set that can be an organization, but it can be also a closed set, a semi-self-containing, whatever. And then we make generate. Then we start from another set, and we generate from this set. We find a function that, given this point, will generate the other point. And so it essentially will give us an arrow. I think I also wrote what the function is later on. So, given a set, I can find an organization. but it's a many-to-one relation. There are many sets that will lead to the same organization. Of course, on one side we have 65,000 sets, on the other side we have only 54 organizations. It has to be a many-to-one. And look over here, and this is another way of representing it. This is an organization. Those two sets all lead to this organization through this function. We color them in the same way. Now, if we look at this, is another kind of system. It's not exactly an ordinary differential equation, but it was the prettiest picture that had attractors over there. And it's discrete, but it works the same. So essentially, different colors leads to different attractors. Wherever you are either, unless you are in those little points just in the middle where, but everything else will lead to those 4 big attractors. So we have something similar over here, and each of those points will lead to an organization. Sometimes it's the same, sometimes it's not. Now, what does this give us from a mathematical point of view? Well, if this is the space of all possible, is this, multidimensional HN, hypercube in n dimension, all the possible sets, and we have an organization, and we have all the elements and we have all the sets that generate the data. Now we can take this set and we can, put it apart. Then we do it for another organization, and then we do it for another organization, then we do it for another organization, until everywhere you are, either you are in an organization or you are into a place that will lead you to an organization. Now, let's speak about the generators, because I spoke about this function and I said, well, you want the generator organization. This is the final set, but essentially, before going there, we need to make one step before, and feel free, this is kind of advanced material. If you are tired, take a nap over here. I'll wake you up at the end of it. Now, in the case of the closure, can you have a generate closed set, where you take a set and you generate a closed set? Well, in this case you don't need it because every set is closed. In this case over here you need it, you can have it, it's there, it's the smallest closed set. It's the smallest closed set that contains that set. So you have that set, you have a lot of other sets, and the smallest of it, which exists and is unique. You can prove it. Exists and it's unique. That set is the generator organization, is the generated set. For semi-self-maintaining set, well, again, here we don't need to do anything. Here is essentially the equivalent. They generate a semi-self-maintaining set. Given every set, you can generate a semi-self-maintaining set as the biggest set inside it. Again, it exists and it's unique. Can be proven, it's basic algebra. But then, for chemistry, you cannot do it. Why you cannot do it? Because it's not unique. Because you can have more than one. And for self-maintenance, same thing. For self-maintenance, it's the same thing, but instead of taking the biggest semi-self-maintaining set inside it, you take the biggest self-maintaining set. And for semi-organization, it exists, but now it's more complex. It's not anymore, we cannot anymore say we just want the biggest or the smallest inside or outside and so on. We actually have to apply the two elements one after the other. So given a set, we first generated the closure of it, and then we generated the self-maintenance. And for all those systems over here, you can always do it. Later on, you cannot do it. Sometimes it's not unique. Sometimes when you do the second step, you lose the first. So you go from a set to a closed set, and from this closed set, you go from this to something which is self-maintenance, but suddenly it's not closed anymore. And so there are complexities over here and difficult things. And if anybody wants to study things and has a background in algebra, please come and see me. I'll tell you how far I've gone, and you can bring it forward. And for organization, is the same thing. You start from a set, you find a closed set, and then you find the self-maintaining set inside. It can be done, it's easy. Fair enough. Now notice one thing. All those systems are the one where I said that you had a lattice. Those are the one where I said you do not have a lattice. If you have a generators, then you can have a lattice. If not, you just have a post set. Those are an extra element for people who maybe already knew this stuff and wanted to add something. Now we use this concept to define a new. We use this to define a new concept, which is the shadow of an organization. So suppose you have an organization over here, and then you have a lot of sets that point to this organization, that generate this organization. Then this whole area is, we'll call it the shadow of this organization. And this organization will have its shadow, this organization will have its shadow. So the shadow of organizations is the sort of the equivalent of the basin of attraction. In fact, you go from the phase space, you have the space of molecules, and here it is, and then you have the fixed point, and you have the organization, and here we are, and we didn't find anything equivalent to the attractor. Yep, that is an open problem. Yep. But we did find something which is equivalent to the basin. It's not exactly a basin of attraction, it's more like a basin around the equivalent of a fixed point. But as I said, this is not exactly the same thing. We are using the concept over here to understand the concept over here, but it's not exactly the same thing. So the equivalent of the basin of attraction, which divide the space, so you know, I'm in the basin of this attractor, and then I go in the basin of this attractor. Well, over here would be the shadow. The set of molecules that generate an organization, and we've seen all this, and as you had your nice colors over here, you have your division of color over here. So let's go back. You have, this is the example we've seen before, this is the 54, and then you have 65,000 sets, 16 dimension, 54 organization. So you have about 1,200 sets that point to each organization. Each of those organizations represent one of those 1,200 sets. What does this mean? That we have finished. What does this mean? That as your system moves around, it will always be in some set somewhere, and it will always have some molecule, but you can always track in which organization is being generated. You can just have one of those that gets alighted, and you know, we are here, we are there. Now the next, so again, what if n is equal to 5,000? Well, I don't care, because I'm only interested in the lattice of organizations, which normally have many, many points less. We don't have 2 elevated to 5,000, much less. I don't take question right now because I'd like to reach the end. Sorry. So, basin of attraction, now we have the trajectory. Well, this is an example that I've been working on, 500 molecules, so 500 dimension, and it's part of a family of 9 factorial by 9 factorial artificial chemistries. This is how it went, which molecules we have time. Red molecules are autocatalytic, so they tend to dominate. Fair enough. All this is quite irrelevant. What is interesting is this. This is the lattice of organizations. It's not the complete lattice of organization. This is as far as I could map it. And I'm getting much better in mapping lattices. And now, sorry, what has happened over here? Now I want you to actually get a glimpse of how this is inside. So we are just going, so each of those is an organization, okay? And what you see over here is a really zoomed out thing of what's over there. There are about, I think, about 2,000 organizations. Now let's go back to the keynote. And here we go. So, this is a little movie. It will last too long, but we can just do a few slides of this. So here is the lattice. You cannot see it. You've seen it before. I just learned to do movies, and I'm still not really good. So now, as time goes by, you can see the organization, the red pointer, which represented the organization that goes around. Okay. Now, are they linked? Is there a continuum while we are studying this? Essentially, we are taking a time scale which is a little bit too long, I found out. So if instead of going one generation after the other, I would go slower, I would actually be able to find how the set moves in the lattice and actually follow it. This is among my future plans. And we are doing some work with Daniel Setter, who is over here, just to study how the system moves in a more continuous way. This is another movie now. If we have a set of molecules, this is the organization generated by this, but suppose I take less than one. Those are other organizations that are being generated. Instead of taking all the molecules, I take all except the least present. I ignore the least present, and then I ignore the other least present, and so on. So if I take only the most popular molecule, I will generate this organization. The two most popular, I will generate this. And the three, I will either generate this or this, and so on. And as this goes on, now we have three colors. Oh, sorry. This was really not meant to happen. Now we have three colors. Some organization will be white, some red, some green. The red one are the one that I'm generating right now. The green one are the sub-organizations that are present but are not being generated. And the white one are the one that I have explored. And as this thing goes, you can see how our map of the whole system, of all the possibilities of the whole system is exploding. And this is not even exploding as it could. It could I could have much more organization and study much more organization. It's just that it was computationally too costly on this machine. On a Mac Mini, it's already better.
Sorry, which was green again?
Green are sub-organizations that I would not generate in this moment, but that in any case are there. Suppose that you have a molecule that is, not very important over there. So I see the system with all the molecules and also this one, or I take this out. But if I only take this molecule, that generates an organization by itself. That organization would not be red because I don't generate it, but still will be green. Okay? And there are a lot of other green organizations that I haven't discovered so far. So, but this has no history, so this one is another version of the same thing with history. Where red are the molecule, the organizations that are present in this moment, and then they become blue as they cool down with time. And as you can see, I'm trying in all possible ways to get this visible. And obviously I need to color better the connection between the organizations. In any case, essentially this is the map of the system. You have studied this system, this is the map. Now you want to know which of those organizations tend to attract. If we're speaking about attractors, some of those will attract, some will not. The movement inside this space is not smooth, is not always the same. So this is the space that we're studying. This is our space of organization. Okay, now I think it's pretty much finished because we've gone through everything. So we've seen phase space, space of molecules, fixed point are organizations. Every fixed point is an instance of an organization. We don't have an equivalent for attractor, but we have an equivalent for a basin of attraction, that is the partition, which is the shadow of an organization. And in this way, you can get the trajectory, which is the movement in the lattice of organization. We studied, there are some papers about this movement where you can see which kind of movement is possible in which kind of system and so on. I invite you to look at my publications. I mean, really, there is no time. You've seen it. It's just not possible. It was important to get the basics out. Oh, no. Sorry. I forgot. Okay, and this is what. So those are some of the papers. Actually, this is the theory, where the theory was presented. And essentially, this is the big paper where most of the thing were generated at that point was presented. My PhD thesis had the whole thing, had this paper as a sub-part of it, and the sub-part were better written, and a lot of other papers, and then there have been some other result later on, and then you have a lot of other papers, and those are papers of applications, and those papers are essentially all papers about applying it to biology and applying it to chemistry and so on. There's very few applying it to proper artificial chemistries, which is a reason of frustration for me. I really invite you to do it. This is something that I left over there in case. Okay, thank you very much. Now I take questions. If there is time.
Yeah, Pietro, it's fascinating talk, thank you. I was interested on the bottom row of your diagram there, when you talked about general chemistry.
Yes.
And for some reason, something about you can't make a lattice or whatever.
Yes.
Is that related to the fact that when you come to general chemistry, in effect there's more or less an infinite number of possible molecules?
Nope. It has nothing to do with the number of molecules. It is related to the fact that some molecules, you can do this with a finite and infinite set. The artificial chemistry, the alchemy system of Fontana had an infinite number of molecules. So that's an example of an infinite one. Your question was not what is it related to. So I'll answer your question.
Okay,
which
well,
is
what is
easier.
it? If you want to say more about it.
Well, the fact is, it's related to the fact that you remember how self-maintaining was defined in a different way if some molecules are being destroyed or are not being destroyed. In all the systems above, the fact that a molecule is being destroyed or not, you can tell it independently of what's around. In chemistry, you cannot. So you can have a molecule which is not being destroyed in a particular system, but it would be destroyed in another system because this molecule by itself does not react with this other, and there is no outflux. But when you introduce a particular molecule, it will interact with that one, and so on. Now, why is this important? Because essentially you cannot have a generator and then the lattice goes, and and then you essentially when you take a set, the biggest self-maintaining might be more than one. It tends to give all sort of nasty problems inside. But the sets exist. It's just that they are not nicely organized. Okay, next question. No, if there is no question, I expect you to have understood it. So I will check in the artificial chemistry's work that has been done if someone is just following the trajectory or someone is actually studying the map and then doing something else. Please.
Yeah, this is because I can't actually catch up and follow at this pace. What's the website so that I can, your website?
Okay,
so I can find all of this?
My name is Pietro Speroni di Fenizio. My website is pietrosperoni.it.
So, yeah, I guess if nobody else is going to ask a question, I'll ask about thermodynamics again. So obviously thermodynamics puts quite big constraints on the types of chemical reactions that can happen. And I was wondering if that makes any particular difference.
I'm sure it makes huge differences. One of the things that we need to understand is that this is a pre-study of system. So you would say that, for example, maybe the system that you're interested in are organizations and are, from a thermodynamic point of view, also feasible. Okay? So it's some sort of requirement.
Yeah.
So, for example, if you go and study the molecule in the metabolism of the E. coli, for example, this was a result that we had at some point, and in 2000, is in the other one, but it doesn't remain fixed. Florian presented it as part of his PhD thesis, and then you had it later on from Alergic Murray the next year. And this is an organization. The metabolism inside the ecology.
Yeah, sure. Yeah.
Now, it might be a special organization because so if you're saying we need to extend the concept of organization to also add so that you have supra-organizations, so that our organization end in plus, they are also, it's not just the stoichiometric metrics, it's not they came from the, I'm absolutely with you. Yeah, it has to be done. I probably will not do it. You're absolutely welcome to do it, and you have my full, even academic support.
And I suppose then another question is space. That you know that the organisation of a cell isn't just a chemical reaction network in a homogeneous system, which is what most of the things that you were talking about were. It's also has the membrane in the spatial representation and stuff. I was just wondering whether there's anything particular you can say about that with this.
Yes, chemical organization at different spatial scales. In Ecal 2007, and it was a poster. A lot of those papers, when I actually present them and in conferences, they reach the point of being posters. I wonder why. Please.
When you were speaking about trajectories, you were talking about the systems moving from one organization, the shadow of one organization into another.
Yeah.
So there's this big phase space of all the different possible states of the system.
Yeah.
And you're describing the trajectory as going from one region to the next.
Yeah.
I'm not sure how you're deciding the sort of size of these regions that it's moving between. So I'm curious how
it's being done in a you go point by point. There is a function that it has been well defined. That you apply this function to the point, and it will give you what the organization is.
Okay. Is it possible for that function to say, I'm not anywhere near an organization?
Nope. It is a partition.
So then, no matter what, it's moving from one region to another region?
Yeah. No, it can also remain in the same region.
Okay. So you've divided the subspace, the phase space into a bunch of different places.
Yeah.
All of the subspace into a bunch of different places. And you're saying it moves from one space
to another?
To another.
Yeah. And I'm also saying that this is actually meaningful.
Okay. Can you elaborate on?
Yes, I can elaborate.
Why
I can elaborate on this. First of all, because from equation point of view, each of those spaces is not. I don't just apply them. How do I calculate this space? I make the closure of a set. Okay, because I make the closure of the set, I'm calculating all the possible molecules that can be generated. So when I am in a particular set, I cannot go somewhere else. I cannot go above. I have to go in the lattice either there or below. So this is already...
Sorry, what's the height axis you're talking about?
The new molecules.
Okay.
I cannot get new molecules that are out of this area. So each of these areas is like they have a membrane, and you cannot go up in this membrane. You can go up if you get an external mutation, but inside you cannot go up. So we moved from a system which has intrinsic novelty to a system which essentially does not have intrinsic novelty. Okay? Now, you also tend to have a membrane below, because although you actually could go down statistically, practically, every molecule that is there can be generated. So you can pretty much assume that they are going to remain there. Yes, you're right, it's not always true. In fact, if you take your system and you put it on a particular point, in time it can go down. It will not go up. Okay? If you're in a point and you're like looking at this from an ordinary differential equation, the attractor will be either in this organization or somewhere below in the organization, in the lattice, in the organization below. You know, the lattice have height. If I go back to the if I go back to the nice picture of the lattice,
Is
Right.
that the exact opposite of what Kaufman says in his stuff about the ever expanding adjacent possible?
I haven't got a clue because I was not able to understand. I followed with great attention that I could not understand it. Essentially, yes, I think so, because but those are formal systems. He was speaking about life in general, life, the universe in general. So I don't know.
Fair enough.
Okay. Now, so essentially you go down. Wherever you are somewhere over here. You've divided into groups, so you are somewhere over here, and then you can either reach this organization or you will go down. And then you stop. So you will, if you take away mutations, it will just reach one point down.
Can it actually go up again? If you imagine a chain of chemical reactions where A makes B, makes C, makes D, makes E, you lose A, so you've gone down, but still you've got that sequence, and sorry, E makes A again, then
Nope.
you go back
Nope.
up again.
Nope. Nope. Not possible. If you have gone through from one to the other, if each of those, imagine that this is not the organization, each of those is one of the shadow. So now you are inside here in one of those shadows. You cannot go up. It's illegal. Without mutations, you cannot go up. It's mathematically impossible.
But that's on the assumption of the chemistry doesn't apply to general chemistry.
No, also to general chemistry. The only thing with general chemistry is that instead of having only one line up,
Yeah, sorry,
you
yeah,
might have more than one.
Yeah, my mistake. Yeah.
Okay? Did you got it?
Yeah, and I understand now what you're saying about how it can't go up and how it
Yeah,
can't
because
go
it's
down.
closed. So this is
Yeah,
a totally impermeable. It is permeable going down.
Yeah,
It's
yeah.
impermeable going up. And going down, we are trying to make it impermeable. That's why we went from semi-self-maintaining to self-maintaining, because we took away the cases where it was just always going down. The semi-self-maintaining, the semi-organizations that are not organizations, you always go down. There is no way that you remain. But in the organization, you can remain there. There is the possibility. That's why it's important. Now, maybe it doesn't, but
I
Okay.
thought general. Sorry, go on.
Sorry, just the last bit to my question. You're saying that the topology of these networks and the motion through it is interesting because of this aspect of it can only fall down. That's what the meaning is of having these different regions.
no, the meaning is that now you have a map where you can follow it, and the map is meaningful. And where you actually can see the whole thing, for example, and say, where you can see this whole, I'm trying to get, okay, it will come up. Sorry, what was your question?
I'm just still trying to understand the meaning behind the map. I understand you divided the space up into a bunch of regions,
Yeah.
and
Well,
what is the benefit of dividing up them into
we've
those
moved
regions?
from a state in which you have those 16 molecule or 500 molecules, and you had no clue about what was going to happen, to a state where you know what are the possible subsystems that can remain. So instead of when you look at this is a nice picture. I should keep this because when this system had 65 possible states, you had no clue what was going on over there. If you're running the system, you are looking at it, and it's impossible. You just see all those molecules going around. While over here you have a map, and you can see where I'm going. And for example, you can start to see that some of those organizations are attractive. From here, you always fall down here, for example. From here, you always fall down here, but from here, you don't go down. This is one part of the theory which leads to the dynamic. So, given this, you actually study how do you move from those organizations. And so, yes, you can move down, but then you have, for example, from here, can you move up? No, without a mutation. But with a mutation, can you move up? You might have a system where even without mutation you cannot move up. In fact, it's quite common. So you might end up having a system like this where not even all the organizations are important. you are only interested maybe in 5 organizations, where everything leads to here, or leads to here, or leads to here. And maybe you know that if you want to go from this state to this state, you need to put send a particular mutation. So essentially, you've transformed this incredible system of 16 or 500 molecules into a finite state machine, where you have the various states which are in the organization. You send a molecule as a signal, and this moves the system from one state to the other. Now this is chemistry. All those systems, you can see them in this way. And it's just algebra. This is the meaningfulness of this.
Okay, thanks.
Okay, you're welcome. You had another question about chemistry. Do we have a time just for the last
Very
question?
quickly, last question, yes.
We can take it offline if need be. I was just thinking, Pietro, I mean, yes, I think what I can see the power of this, because you're essentially reducing your search space based on algebra. That's what I've understood from this.
Yeah,
and
just
instead of
using algebra,
solving
that's important.
gazillions of systems of ODEs, you're reducing it. But I wanted to pick up on the point you said there, where you can't go down.
Yep.
But in general chemistry, you can't go up.
Yeah.
In general chemistry, surely, even if you start from the most basic elements, you can generate anything, can't you? If I have carbon, nitrogen, hydrogen, oxygen.
That's a very interesting point. I presented a paper in just this year at ECO. It was a poster at ECO, which presented that if you have a base, if you have an artificial chemistry where you have a base, then essentially it becomes pretty much useless, this, because you are just jumping from one place to the other. Every mutation will just make you jump. But not all artificial chemistries are like this.
Yes.
Some are and some are not.
Yes.
In fact, if you want to have evolution and you want to have a proper growth where from one goes to the other, this is the reason why Walter Fontana was not able to get evolution, because it is very easy in the lambda calculus to have a base. And when I did it with combinators, you remember, Inman, it was a similar problem. I mean, we did not reach the part of actually following on. But then I reached it following on, and it was a similar problem. It would not have some sort of growth or little movement and exploring the space. It would jump from one place to the other all the time. Why? Because there is a base. If there is a base of the mutation, if the mutation can send in a base of the space, you are, it becomes, yes, it's a map, but you're jumping from one place to the other like a little rabbit. If this is not the case, then you really can follow it. I think now we're...
There's scope for all questions offline if we adjourn to the IDS bar.
Wonderful.
Okay. So let's thank.
Hello. Good, just a second.